afternoon. I'm Marco Calderisi from Kode. We are a small enterprise based in Pisa. We were born in 2012, and at the moment we are more or less 15 people. We are all data passionate, and the core business of Kode is data analysis. So we use different techniques coming from data mining, machine learning, data visualization, and in the last years also from deep learning to do things. Our approach is data-driven. It means that, as you know, this is a typical approach for the machine learning paradigm, which is we got some input, some output, and then we look for the rules of the system using our algorithms. Usually we start from very messy and incomplete data, unstructured data. It means data coming from different sources and like images or also PDF or Excel file, database, everything else. Our approach is this one. We try to cover all the chain value of the data analysis process, from the acquisition of the data to the visualization of the results. It means that we collect data from different sources. We store them in database. We use different kinds of databases. It depends on the need. We do a big part of cleaning and contextualizing of the data, and then we do the part that we like best, which is the analysis one. This is usually an offline process, I would say, like taking the data and trying to find the best model, the best algorithm to reach the objective, the aim that we have, and then try to deploy the algorithm into something that can be used, I don't know, real time or something like that. And but we don't have end there. We go to the visualizing step also. It means producing some dashboard or software web application that let the final user use the work that we have done, even if he's not a data scientist or something like that. These are our reference markets. We work mainly in this industry sector, healthcare, and also in the data visualization. These are some research projects in which we are involved. These are the InGene and Genomics project founded by the Tuscany region, while the last one is funded by the Sardinia region. The first one is a project that is about looking for correlation between genotype and phenotype to have a better understanding of some pathologies that regard the musculoskeletal apparatus. So in this project we do a few things. The first one is the analysis of a genetic data variants, trying to understand which are the variants that are responsible of or at least a marker of the pathology. And the other work that we do is we study signals from accelerometer. They are installed on the arms of the patient in order to do a better diagnosis of the movement. And in this project there are some research centers like the Fisiologia Clinica, the Institute of Biorobotics of Sant'Anna, and the Fondazione Stella Maris. The other project, which is called Genomics, is a project that we are carrying out with Scuola Normale Superiore, the Nest Institute, Fondazione Pisa per la Scienza, the IIT, and another institute of CNR here in Florence. And the aim is to have an early diagnosis of the glioblastoma, trying to identify as soon as possible the biomarker that indicates this kind problem. And what we do in this project is we try we develop a software that let the researcher to run some algorithms that help them in lowering the detection limit of the instrument that they developed. The last one is called Leaf, and this is a software platform that try to get some value out of data taken from a quick analysis done into chemist shop or places like that. But those projects are projects that are not publicly funded. The first one is a project we are doing with a big pharma, and well, in this project we have to understand to calculate the quality of life index for a patient who suffer of heart failure, and we have to calculate this index using accelerometer data that were by those patients with patches or bracelets. And the other one is a project that we are doing with another enterprise which is based in Navacchio near Pisa, and they build this device that is able to analyze air, but they collect lots of data, but after a while they decide to look for the information that is inside those data. So our collaboration started from there. Okay, so then I want to show you 3 case studies on which we are working. The first one is a work about image recognition. We study biopsies to diagnose the mitochondriopathy, and we use deep learning techniques. The other one is a work which is in the biomarker detection things field, and this is the one that we are conducting into the Genomics project. And so in this project we use very easy but very useful techniques like normal PCA and analysis of variance of the scores. And in the last one, which is Genomics, this is the exploration of the genomic database. We use another supervised technique, which is the multidimensional scaling, and this is an instrument that can help the clinician to explore the data that they collect with the NGS. So the first one, the image recognition project, we need to identify automatically and efficiently rugged red fibers in biopsies. So usually the process is I take let's say picture, an image of the biopsy, and the clinician looking at the image calculate the area which is with this reg fiber. And so we developed this algorithm to automate the procedure, and the performances are pretty good. This is the image. We wanted to do some segmentation, but we are still at the early stage of the work, so we prefer to divide the images in a little square, I would say, and we classify each square to see if there is a red fiber in it or not. And the algorithm is divided into 2 steps. The first one is the identification of the tissue and part of the image which is not useful, and the second step is the identification of the part which is damaged. And in order to do this, we analyze the images, but we also analyze some features that we derive from the images. More or less 82 features per image. And because the algorithm that we use is this one, is a sort of a hybrid deep learning algorithm that has a part is a CNN net, and the other part is a dense net. And we concatenate those nets at the end to improve the performances both the nets. And we developed it, and so we also wanted to build something that was very, very fast, and we compare it with other well-known algorithms like ResNet and Inception, things like that. Well, for this kind of work, the algorithm that we developed is faster than the others. Okay, so this is the other work. We need to identify those biomarkers coming from brain in order to understand if the patient has the glioblastoma or not. And so the NEST Institute developed a lab-on-chip, which is also patented now. It's called Breaker, and we developed the software that gets the signals from the breaker and try to help the user to find also very little differences between the reference signal and the pathologic signal. As you may see, there are two spectra on this figure. They seem exactly the same, but they're not, because the first one is the reference control, the reference spectra, and the other one is the spectra with the pathology.
The software, you order the software.
Yeah.
Is the you or is the
No, the software is ours, and we are also trying. No, this is no. We work in this project as a partner. So we work for free for 2 years. But now we are setting up a spin-off startup together.
So you are
in order to put together things, the lab and chip and together. So, as I say, the spectra looks more or less the same, but they are not. You can see the two clusters here, there, and on this figure, already you can see which are the parts of the spectra that are responsible for the differences, and this is the box plot of the score plot that can show a significant difference between those two set of samples. The other work is a gene explorer. We work with Calderisi to do this. These are data coming from an NGS, a next generation sequencing instrument. And well, when we arrived, they were used to analyze no more than 8 samples per time because of a license reason and something like that. And they were doing all the procedure of looking at variants manually using an Excel file. So it was nearly impossible to achieve anything, I have to say, because they can analyze up to 20,000 variants. So we produced this software, which is built on a non-multidimensional scaling algorithm, and we just take the data and we do this analyze, and so you can see two clusters here corresponding to the two samples of data. These are the variants that are responsible for this clustering, and of course the variants that in the middle are the more frequent variants that are in human beings. So you can refine your search not only on the number of variants, number of genes, but also on the frequency. Doing something like this, you take some variants out, and then you can see which variants are in samples and vice versa. And at the end, you receive a report. This is just a tool that you can use to explore the data. It doesn't give you a classification or suggestion or anything like that. But anyway, it's better than an Excel files with hundreds of thousands of numbers. So that's all. This is our address.
Thank you.
Thank you.